Hi, I'm Noah. Welcome to our Math Interest Group talk. So in this talk, we'll be building off of our main SMT talk. So you might want to consult that video first, though we'll begin with a review. This talk will focus on some technical considerations about the space we define. Our model was inspired by similarities between different fields' use of the discrete Fourier transform. So all the way at the right of this diagram, we show what we call the PC-DFT, that is the DFT on pitch class space, which is one of the better known models in mathematical music theory recently for chord quality. Top left center, we show the DFT's best known use in audio engineering, where given a waveform, it obtains the pitch spectrum. For some purposes, though, audio engineers will apply a second DFT onto this frequency data to obtain what's called the cepstrum. This is useful for computational timbre identification. Our approach then takes note that both the cepstrum and the PC-DFT are doing a DFT on some sort of pitch data, so we can combine them. Like the cepstrum, we don't use octave equivalents, but borrowing from the PC-DFT's chord quality, we do use actual pitches, as notated. What we end up with is a study of chord spacing that somehow combines chord quality and timbre. As I'm sure most of you know, the DFT, or discrete Fourier transform, takes in a signal and outputs how strong various periodicities are. The usual PC-DFT, for example, starts on 12 pitch classes. We end up with 12 components. We have to discard half because of the Nyquist effect, so then we get 6 distinct components in the end. The P-DFT consists of the same approach, but on pitch space, without octave equivalents. We use a MIDI keyboard, so we have pitches 0 to 127. To avoid wraparound effects, we zero pad it, so we end up with 256 items in this vector. We put it through the DFT, and then throw out half of those components, so end up with 128 again. So the first question to ask is, does this model actually tell us anything we don't already know? So to answer that, we ran some correlations between all possible P and PC-DFT components on 1,000 randomly generated chords. So we see strong correlations between each PC-DFT component and exactly one corresponding P-DFT component. This happens when the components correspond to the same interval. For example, in orange, an octave is PC component 12 over 12, or 1, but P-DFT component 256 over 12, approximately 21. So many of the other components between these peaks or at the low end do seem to offer something new.
Hi, I'm Matt. By taking the P-DFT of a chord, we can therefore study both the PC-DFT's chord quality from music theory, as well as the timbre that chord spacings bring. For example, in this chord from Sarjahos for Blendungen, we see that the lower components of the P-DFT detect the widely spaced tenths. The peak around component 77 also supports minor thirds and tenths as well. In our Mitsness and SMT paper, we compare the distance between chords by taking the Euclidean distance between their P-DFTs. But since our model is based in theory, in the presentation here we decided to see how it correlated with subject responses. So we used data from Kuzi 2005. Kuzi studied subject responses for 4 different set classes with 4 different chord spacings. Subjects were asked to rate chord proximity using words including closeness, resemblance, and similarity on a 7-step scale. Each chord was paired with every other except for those that shared the same chord span, so the largest spans were not paired with the largest spans. This made for 106 different chord pairings. The study used both musically trained and less trained subjects, but since the trained subjects were more consistent, we'll restrict our discussion to trained subject responses. Kuzi then compared subject ratings to set class similarity measures, including ASIM, ICV-SIM, ISIM2, SAT-SIM, CSAT-SIM, etc., and found that correlations between the two were rather low, peaking at R equals 0.43 for CSAT-SIM. Instead, Kuzi found that the estimated distance between two chords increased with the difference in chord span, a feature that pitch class similarity measures wouldn't detect. So, for example, these two chords were rated far apart even though they're the same PC set, and these two were close. Seeing that the P-DFT recognizes spacing, we assumed that it would correlate with subject responses better. But it turns out that using all components, the correlation isn't that great at Pearson's R equals 0.38. So we dug into the P-DFT to see how each component factors into the subject predictions. As shown here, we see that to Kuzi's subject responses, certain components are better at predicting subject responses than others. Following the idea that some components matter more, we did a form of stepwise regression that we're calling the spark-joy method to trim the P-DFT's components to only the ones that positively impact the correlation. Now, obviously, this is all post-hoc, so we're not making any predictive claims here, but we were able to get a correlation value of 0.74, which is much higher than any other pitch class similarity measure. We've also just started to explore optimization of P-DFT components for predictive results, but we'll have to explore other subject studies and responses since Kuzu's experiment was designed in a post-tonal setting, and that's what we've been training the model on.
These ideas, selecting important components and measuring chord similarity, raise interesting formal issues in our mathematical space, even without reference to any subjects. So this slide compares different ways of measuring distance between chord pairs in these spaces. So each of these boxes compares P-DFT and PC distance, but using some different choice of P-DFT components and a different choice of the distance metric. Each dot represents a pair of chords. The color gets brighter as it gets further from a perfect ideal correlation. You can see that the correlation is stronger when we only use higher P-DFT components. That's no surprise given what we looked at earlier. You can also see that there's a strong effect of whether we use a Euclidean or cosine distance metric even within the same choice of components. The Euclidean measure more closely follows Callender's pioneering work on DFTs, but cosine distance is more common in recent machine learning approaches. Even though we do normalize our vectors before Euclidean distance, you can still see quite a bit of difference. In particular, you can see that the cosine distances tend to cluster closer towards the x and y axes, whereas Euclidean distance tends to jump from 0 a bit more starkly. You can also see that the correlations are substantially stronger for Euclidean distance. We would appreciate any insights you might have on how the difference between these distance metrics might help us better understand the space that we're studying.